Okay, new concept, variation of parameters, but let's quickly review what happened. What happened was this. This technique is known as the undetermined coefficient. So we solve the homogeneous equation first, when this side is 0, and then this is what we call g of x here. So if that's a polynomial, for a particular solution, we try polynomial. If the other side is e to the something, then of course we try e to the something. Same thing that would give us, if you take a derivative, something that looks like this. And then if the other side is sine or cosine, then we try a combination of sine and cosine, because once you take a derivative of those, it'll still give us sine and cosine, right? And then, of course, that's a combination of e to the something and sine and cosine. Then we try those separately and just add them up. So that's what happened so far. So good? Okay. What happens then today if the other side is tangent? Do you know any function that you take a derivative and that gives you a tangent? Because I sure don't. So you do not want to try some combination of tangent and secant u. That's unthinkable now, isn't it? Because things get very complicated. So far, whatever we have been trying, polynomials get simpler once you take a derivative. Sine and cosine still remain as sine and cosine. E to the something still remain as e to the something. But something like tangent, it gets very, very ugly really fast. So you don't want to do such a thing. So here's a new technique. Okay, I'll just briefly run through. Oh, by the way, in previous cases, if you use this technique, it still works. But the reason it works is very difficult to see, so I'll show it with an example first. But like before, we solve the homogeneous equation, and we get these two, y1 and y2, right? And then we are going to add this particular solution. But the way we do particular solution is, you see that this particular solution is exactly same as this, except C1 and C2, we are just calling it some kind of unknown function u and v. And then you think, how do you know that works, right? Because mathematicians that came before us has figured it out as the only best answer I could give. I'm not sure why this thing works, but it works. Then you take a derivative, and we have to do one more step. We have to set this first thing to 0. Why? Because if you don't, it gets too complicated, makes our life miserable, and we have no hope. So we'll only consider the case if this is 0. And if this is not, then this method fails. Let's just put it that way. And miraculously, it works out. Okay? Like, that makes no sense. So why don't I just take this example, and then we'll go back to that theory. Okay? So let's do this. So first, as always, we solve the homogeneous equation, right? So homogeneous equation, of course, is y double prime, in this case, plus y is equal to 0, 8. And then we are going to try y is equal to e to the rx, as always. And then we can skip this step. Second derivative becomes this. And then first derivative is just this, is equal to 0. So we have e to the rx common factor, and then we'll have r squared plus 1 is equal to 0, 8. So from there, r is equal to plus or minus I. So my particular solution, well, common solution is, we can write it like this, e to the ix plus e to the negative ix, but we rather want to work with this form. Using Euler's formula. So far so good? So far so good here. Now, for a particular solution, this is where things get weird, okay? For particular solution of this thing, we're going to try y particular is equal to, instead of a and b, we just call this u, which is a function, plus v, which is a function, and see if this works. And it's the weirdest thing. I mean, I couldn't believe it when I first saw it. Like, really? That works? So it does. Okay, so in order to plug it into the differential equation, this one will take our time and take on derivative. And this is a product rule. Okay, I'm going to write the product rule in a little weird order. U prime, cosine x, and I usually do u and then negative sine x, right? But I'm going to write this first. U prime, sine x, and then the other side, okay? So plus u, it will turn out to be minus u and then sine x, right? So the second half of the product rule of that one is here, good? And second half of the product rule of that one will be plus v and then cosine of x. Are you with me so far? Further, this thing, we're going to set it to 0. And then one of the reasons that we want to set it to 0 is if it's not 0, we are going to take another derivative here, right? And this thing gets crazy. Can you imagine if this is not 0, then you have a u double prime cosine x and then another product rule, right? Wow, I sure don't know how to handle that. Okay, so we only consider the case where this thing miraculously cancels out and becomes 0. Then at least we don't have to worry about u double prime, v double prime, okay? So we'll just take a derivative of this, okay? So derivative of this now, so u prime again, so we have negative u prime, that's small, why did I write so small? So we have, oh really? Negative u prime, and then cosine of x, so that's it. Okay. And then my plus b. Did I write cosine? I mean sine, because I took the derivative of the first. Sine of x and plus b prime cosine of x, the first part, right? And then second half of the product rule, so this now becomes minus u of cosine of x, and this becomes minus b of sine of x. Are you with me? Are you with me? Now we are going to substitute that into our original differential equation, which was this. W prime plus y is equal to tangent x. Okay? So let's see what that is. So we have y double prime plus y is equal to tangent x. Okay, let's plug it in. Do I have enough? No, I just wrote it. So I have all of this, right? Oh, this is a computer. I can do copy and paste. So I have all of that here. I have this much. No, not that one, this one. I'll just copy that one because that's written differently. Plus u cosine of x plus v sine of x is equal to tangent x. And then you're thinking, oh, that's complicated. How does that help us, right? Watch the magic here. Do you see that this thing cancels this thing? And then this thing cancels this thing? Whoa! How did we get so lucky? No, it's not luck. This method is designed to do that. And I'm gonna, well, written up proof. I'm gonna try to convince you why this is the way, but it's designed to do that. Okay? So it got a lot easier now, right? So what we have left is this negative u prime sine of x plus v prime cosine of x is equal to tangent x. It looks like we have still two unknowns, right? U prime and v prime. It's kind of like systems of equation, but we need a second equation in order to do systems of equation. Where does the second equation come from? Does anybody see second equation from what we have so far? No? Yes? No? Maybe? It comes from this thing. Remember we set this thing to 0? That is an equation, isn't it? So that's your second equation. Comma, and then u prime cosine of x plus v prime sine of x is equal to 0. We have systems of equation. You get it? The comma looks too much in the middle. I don't know why I'm like this, but I am like this, okay? Now, there is no orthodox way of solving this, but hey, let's solve this in terms of u and then plug it in here, hey? Okay, let's do that. So u here, u prime here is negative, right? V prime and sine over cosine, is that tangent? Oh, there's your tangent. Tangent. Huh. Okay. Then we're going to substitute this into that equation. Okay. So wherever I see u prime, I'm going to put negative v prime tangent x. Let's see what we get. Okay. So here, u prime negative v prime, so this becomes positive v prime now, right? And sine x times tangent. Tangent is sine over cosine already, isn't it? So what I have is sine squared x over cosine x. You with me? Plus v prime cosine x is equal to tangent x. Too much trick algebra? Why don't I multiply cosine x on both sides? And then, so I will have v prime sine squared x plus v prime cosine squared x. Ain't that convenient? What is tangent times cosine? Okay, fine. What do you have on the left-hand side? Tell me you know that much. What is this? This is just v prime. Sine squared plus cosine squared is 1. Yeah. Is equal to sine x. How about that? That is convenient now, isn't it? So, antiderivative of this, because we really want v, which is a function of x, right, is negative cosine of x. How about that? We are still yet to find u. Okay, u here, well, we don't know what u is, but we know what u prime is the negative v prime tangent x. So now we're going to take this expression and substitute it right here, okay? So let's see what happens. So u prime, I'm going to do it with red color. So u prime here becomes negative v prime. I already have v prime. I already know what v prime is. Negative sine of x here, okay? So do you see that this is a sine squared of x over cosine of x then? Say yes. How the heck are we going to integrate this thing? Yes. Huh? Sine square. What is sine square equal to? So do you agree this is the thingy with a negative sign? Good. Okay, now we split this. So if we split it, first one gives you cosine of x, and second one gives you secant. And hopefully all of you remember how to integrate secant x. You want me to show you? How many of you like to review how to integrate secant of x? Hand or virtual hand. Otherwise, I just write down the answer. Okay, just an answer it is. So this thingy now becomes sine of x minus ln absolute value secant of x plus tangent of x, right? That you all remember now? Look, we have found u and v. Okay, so I'm gonna write down the particular solution. Particular solution, remember, was this: u times, it was cosine first, right? Plus v times sine of x, wasn't it? So let's substitute. So I have, oh, it's a computer, that here plus v negative cosine x, right? Negative cosine x and sine of x. So for second, I think I missed something. What did I miss? This thingy times cosine of x, right? So I forgot to multiply by cosine of x. Push it to the right. So this thingy times cosine of x and minus like this and cosine of x here. Now I got everything. Good. Wait a minute, it gets even better, right? This one is purely log. Those two cancel, right? So we just have this left. So this is negative ln x ln secant x plus tangent x times cosine of x. Okay, so what's my all of the solution? That should be y is equal to, first, if this one is still there, cosine of x plus b sine of x, and then this particular solution that we just found. Dang, huh? That's not such an easy thing to swallow now. So why does it work? How does it work? Who came up with this stuff? Okay, so let's try to, well, let me try to convince you of the theory, okay? So let's recap quickly. We found the common solution with a homogeneous equation, right? And then the coefficients, right, constants, we just converted into unknown functions. Take a derivative and conveniently set this to 0. And whatever is left, we take another derivative and plug it back into the differential equation, and miracle happens. This cancels out, right? And I'm going to have to convince you why it should always cancel. And whatever's left is a systems of equation. You solve however you can, integrate, then you get your unknown functions. Plug it back into this, and then you just add them up. Okay? Now, here's why, the theory behind why this thing works the way it does, okay? So this g of x is our tangent here. Tangent, this tangent is this g of x, okay? So we found the common solution from the homogeneous equation, correct? And this c1 and c2, which I call a and b, we replace it with unknown function u and v. So far so good. And then we took a first derivative and we have a product rule as such. And this one we set it to 0. Whatever's left, we took another derivative. So we have this, which is exactly this thing. You know what I'm saying? It doesn't look like it, but this cosine of x is this thing double prime, isn't it? Cosine, sine, negative cosine, negative sine is the y particular double prime, eh? Good? With me? Okay. So once you have this, now we plug it into the differential equation. Remember, the differential equation looks like this. That thingy. So this thingy goes in here, that's this whole thing. And that thingy, because we set this to 0, goes into this, so it has this, right? And c times y is this whole thing, goes in here. So far so good. Like terms. So u appears here and here, right? So this is u, oh, there's u, so we distribute, that's u, y double prime, and then that's it, and then here's u, so b of y prime, and then here's u, c, right? So u common factor and those three. Good. Likewise, b appears here. Here's a b, so that's the first term, a times y double prime, b common factor. Here's where b is, so b y prime, and then c y. Good. And plus whatever's left. This is whatever's left, this term, right? Now, magic happened, right? Things got canceled out. Why does it cancel? Let's just look at this. Why does it look so familiar? This is the left-hand side of this. But then let's remember what y is. Y is the solution to this homogeneous, right? y1 and y2. So we actually found the solution to this, meaning this whole thing is 0, isn't it? It comes from that thing. That's why it's designed to cancel out. It'll always cancel. And then likewise, this is a solution to the differential equation, meaning once you plug it into this differential equation, it gives you 0. So this becomes 0 and that becomes 0. That's what the cancellation is about. And then only thing that's left is this term. Right? That term in our example, after the cancellation is this. You get it? So that term now is equal to the other side, which was our tangent. And then remember this thing, we set it to 0, is right here. And these two gives us systems of equation. So here we eliminate u prime by solving it, right? Sine, cosine over cosine. And then plug it in back in here. And then rest is just algebra / calculus. Well, this is just algebra. I didn't integrate it. But so we have this ugly expression, but it's not, hopefully not as ugly. And then it's just your integration technique. Can you integrate this now? You get it? So hopefully you're convinced that this should work. Miracle always happen. Okay. Any questions?